So the second part is going to be to talk about how we can use OpenMP to program accelerators. For example, program GPUs, or, or if we want to program specialized units like vectorization units in the CPU. And then we're going to talk a little bit more about what is the future of OpenMP and what else we're going to be seeing as we see more implementations of OpenMP 5.0. So one of the things is we started to support accelerators in OpenMP since OpenMP 4.0 and 4.5. So the way it is supported is through the target directive that we have, and OpenMP 4 and 5 covers many aspects. Target just being one of the new features in that specification. And my recommendation is always to look at the OpenMP 4.5 to look at the latest support for target or accelerators, and then keep an eye on the upcoming 5.0 implementations that improves the way target works on the devices. OpenMP is designed to work so that you can have a host where typically it could be a multi-core architecture, and then you can have like an accelerator or multiple accelerators. And the whole idea is that the accelerator model can help you to define basically the computations that you want to offload to these devices, and then you can use the directives to program them efficiently and coordinate not only the computations but also the data. The abstraction model for the accelerator that we see in OpenMP is based on OpenMP Target, where we basically define a device as a logical execution unit that is an accelerator. So from the point of view of OpenMP, an accelerator is definitely, it's kind of agnostic of the architecture. So it's basically a device where we want to offload computations. And that device is going to have a data environment that you're going to use to move data to that device. And then we have this host-centric model where we can use the host or wherever you have for example, the multi-cores that you can use to offload computations or create data environments into these devices. And then as the computation progresses, basically there's going to be synchronizations between the host and the device. And these are things that we can do with the OpenMP Target directive. This is a summary of what we have in OpenMP 4.5. I just want to make a note that we have already OpenMP 5.0 available that also supports Target, but the implementations are still catching up. So as of today, most of the compilers that support Target supports the OpenMP 4.5 specification. So that's why we're going to be focusing on that today. And here is a quick summary about the different types of directives, where we have directives that can be used to define regions of code that we want to execute in the device, or we can have directives that can help us to manage the data environment on the device. Basically, if we want to move data to the device or update data from the device to the host and so on. And those are the set of directives that you see here. And then we have other directives that we can use whenever we are already executing in the device, where basically we can specify the parallelism and how we're going to work sharing the threads within the device. And then we can use that to divide and work share the computations to the different threads. And then we have a set of calls that we can invoke, just like an API, a runtime call from the host, that we can gather information about the device, or on some of them can also be called within the target region of the accelerator. And then we have a set of environment variables that can help us to control things like what's the default device that we want to use. Like, for example, if we have multiple accelerators in a node, we can pick what's the default one, or what is the thread limit that we want to have on a given accelerator, for example. So basically, the whole idea of OpenMP Target is that we're on the assumption that many codes will have already an existing form of directives, like, for example, OMP parallel do, for example, or parallel region and work sharing. And one of the natural progressions is like, okay, I want to offload that region of code to a device. And the first thing that you need to do is to create basically a target region. And basically, the whole idea is like you scope the region of computations that you want to offload to a device, and then specify what is the data that you want to move to the device, or what's the data you want to copy back from the device to the host. So if you have a traditional OpenMP parallel do and you put, for example, OMP target around it, then you're going to start accomplishing that goal, where basically that target will do an initialization of the device. It will initialize the state of the device, create a complete an OpenMP environment in that device, and then it will start allocating the variables in the device data environment. And then once those variables are allocated and created in the device, then it's going to create a copy where basically we're going to copy the data that is in the host, and then we're going to copy it into the device. And as soon as that happens, then we're ready to start the execution of the data, the execution of the code in the device, where, as I mentioned before, it's a completely new OpenMP environment in the accelerator, where we start executing with one thread or one initial thread, and then basically we can specify, that parallel region that you see there, is going to spawn threads, and then we can use those threads to basically work share the computations and between the threads in the devices, and then do synchronization in here, and then we complete the region that we want to offload. And then as soon as we complete that piece, then, for example, in this case, the data environment specifies that, okay, now we want to copy the data back from the host, from the device to the host. In this case, it will be this variable, and then at the end, when that transfer is complete, it will deallocate any data or destroy the data environment that we have in the device, so that we can continue the execution in the host using the host thread. So the whole idea here is like, when you think about what is an OpenMP target, a region is basically you pretty much starting a new OpenMP environment in an accelerator. And that also creates a data environment there, and basically that's where you want to use. So you use that to manage the data between the host and the device, and also anything you specify inside the target region, that is going to be executed in the accelerator. This is just reiterating again that we have this target region, but we also have those target regions also have a data environment. And so the data environment basically is what we use to map data between the host and the device. And that's how we specify, what data we want to copy in or copy out, or just allocate in the device, and so on. And so that's an important concept. Here, I just want to mention that when you use OMP Target, you are basically specifying a data environment and also a target region, basically some code that you want to execute in the accelerator. So you're doing both things. But you can separate both things by, for example, using a directive, for example, that only deals with data environments, where we basically specify OMP target data. So when you use that, you're just dealing with the data environment of the device. And then, so what that means is that you use the sort of constructs to basically synchronize the data between the host and the device, or vice versa. But whatever you have in here inside that region, for example, inside that the target data could be a code that executes in the host, or you can encounter another target region that where you want to actually do the offload of the computations, but there's going to be already some data already available in the device. So, so we have different directives that help us to control not only the computations, but also the data environment. And those target data directives, they can be nested. So you can have a target data nested inside another target data, and so on. There are some rules on how we treat the data that has been mapped to the devices, especially if it's the same device, where we use something what we call reference count to determine, if the data is already available in the device, and when can we do when we control the transfer to and from the device. I will see an example of that. And then we have other sort of directives where we can use to control also the data environment, but we can define it as a global scope. Like, for example, you have some global data in your code that you want to map to the accelerator or to a device. You can use OMP declare target, and then basically you can use that to specify that this is a data that I want to make it available in the accelerator that is global, is in the declaration space, in the global section of your program. And you can also use declare target to embed also entire functions that you want to have in that you want to that you're going to have in the accelerator. One of the other interesting data environment directive is the Pragma OMP enter exit data, and this is meant for codes whenever we want to define those data regions, and they are not necessarily has to be like structured, like for example in here where you have like a lexical scope here with a begin and the end of the brackets. In this case, you can create these data environments dynamically. For example, you can say Pragma entered a data map, for example, in one section of your code, and then later on you can do an OMP exit data. For example, you exit the data environment for a specific accelerator. And this unstructured piece is especially useful when you have, for example, codes or like different in your applications. You have like routines that does the initialization of data, other routines that they do the computations, and then other routines that basically are retrieving the data, basically, or the finalization of the data. So you can use that that way, and also it's important for programming models like C++, where you have constructors, destructors, and you can use and define. You can create these data environments using those things. This is just pretty much very simple, the accelerator model, where we can map the target either to systems that they have distributed memory between the host and the accelerator. Basically, for example, systems that they have, the accelerator has its own memory. We can basically use that, or in systems where we have, like, for example, unified memory, where like multiple accelerators and are sharing the same memory as the host, we can use the OpenMP Target as well. So it's agnostic a little bit of the underlying architecture on how the accelerators are configured, and this is important for the latest types of accelerators that we have. For example, GPUs that supports a unified shared memory. So you can use this for those sort of environments. This is just some device types. Basically, whenever you are controlling your data environment, you can use this to control, basically, if you want to allocate data in the accelerator or copy data to or from, and so on. And there are some rules here about reference counts that we can use to basically specify how many times is a variable is seen inside a data environment and what to do about that. There are some examples of that. Here, yes, whenever a variable is encountered in a target data construct or a target construct and is being mapped, that variable, the reference count is increased by 1, and then then basically whenever you encounter more data regions that tries to map these variables, it will continue increasing that reference count, but only when the reference count is goes from 0 to 1, that's when we're gonna do data transfers using these target data directives. So so the same thing when we're copying data out when the reference count goes from 1 to 0. So for example, in this case, we have a target data where we're looking at the environment and we're mapping one variable, but then we're nesting to target data clauses, directives, and then we can see that we're also mapping the variable C here. But in this case, as soon as we do this first map, the reference count of C is going to become 1. And then we see this map and the reference count is going to become 2. So this from data is never going to be, so there's not going to be, this is going to be ignored by the runtime. So there's not going to be no data transfer in this case because the data has been already been mapped in this case. So if you really want to do any data transfers for these scenarios, you have to use the update directive in OpenMP. Here are some rules about the default mappings of variables. Whenever you specify an OpenMP target, arrays, for example, are mapped to accelerators, are mapped to the devices as to and from. That basically there's going to be copy to or from the device from the beginning. Scalars are going to become first private. Pointers, if you're just mapping the pointer itself, they're going to be initialized to null. And then you can shape pointers using a notation that says the beginning, the offset, and the length of what the pointer is pointing to, and then you can specify that to basically define how your variables are going to be mapped or copied to the accelerator. The other thing to keep in mind is like another mechanisms to transfer data between host and the device is using the update. So for example, when your data is already in the accelerator and the only thing you want to do is to transfer data to and from the device, then you can use the target update, and those directives are called from the host. And you can basically do that sort of synchronization there. Here is just basically a summary of what we discussed in the previous slide, that whenever you enter a target region, you start with an initial thread, and then you can create teams of threads. And these teams of threads, each team within a thread, they can synchronize, just like you synchronize in the host with all possible synchronizations like locks, barriers, and so on. But one of the restrictions whenever you create teams in a device is that you cannot synchronize across teams, or you can only synchronize within the team. And this is something to keep in mind whenever you are writing code, because synchronizations can be difficult to do whenever you are trying to do things across teams. Usually the synchronization happens when you finish the target region, because at that point, all the teams can synchronize. Once you create teams, you can basically distribute the work across the teams. And this is kind of like similar. It works very similar to the work sharing, to the loop work sharing directive, where we can have a static scheduling across the different teams, where iterations can be scheduled evenly across the teams and so on. And then that's how you distribute the computations. And this is just an example of how we can use all together the target region, the teams. You can distribute you create those teams and distribute those iterations across the teams. And then within a team, we can basically create threads, and then those threads will execute work and can synchronize, and then and so on. And basically, you can create multiple levels of parallelism using these constructs. One thing to make sure is that you always, whenever you write code in OpenMP, you want to write it, since you can target multiple accelerators, multiple types of things, you want to be able to write as portable code as possible. And if you have a smart compiler or runtime, they should be able to automatically pick for you the correct number of teams, the schedule for the teams, for the distribute, the thread limit that you will see for each parallel region, or the number of threads in the parallel region, the length of the schedule for the parallel loop, for example, or the SIMD length that you want to use. And this is very important for that. But if not, you can tune those parameters in your OpenMP application, but then it started to become more specific to an accelerator. You can combine target constructs with tasks, and this is an important concept that we want to keep an eye. So because that will allow you to synchronize things between the host and the device. And you can and basically offload computations and do a coordination and orchestration between things that you're going to compute in the host and the device. And you can also use this across multiple devices. And the whole idea is that this will help you to hide latencies or hide wait times so that you can basically continue the computations and use the resources efficiently. It is important that to tune a lot the code that you define in the target region, because it's important. You can see different types of performance. So once you write the accelerator code, you might have to spend some time tuning it. So if you get bad performance, just keep tuning the code. The SIMD clause, this clause is a little bit independent from the target, because this one can be used also in the host. That can be used to vectorize the loops in your code. These are some directives that could give you good performance. Like, for example, you want to align the data that you want to offload to the vectorization unit or the SIMD unit, and you can get good performance by using it. And the whole idea of this directive is to also standardize the way we're specifying vectorization in an application. And you can use this SIMD clause, as I said, in the host, or you can also use it in the target region. And the implementations will map it to the corresponding threads, they will execute in SIMD type of parallelism. And you can also call functions within that. There is an example that we can go over that it's in there, where it shows a Jacobi code that has been ported to OpenMP 4.5 offload, and you can try it and run it and see how that performs. Now, just very quickly, talking about OpenMP 5.0, what's important and what you need to keep an eye on. These are a summary of the features that we have there, and the new things. And the most important things are for accelerators are that we're going to be able to use a unified memory, and also the way we specify loops, and that will help the loop construct that we have to do that. So, for example, the loop construct, basically we can, instead of being specifying pragma OMP4 or pragma OMP SIMD or pragma OMP task loop, depending on where you are within a target region or not, if you just use OpenMP loop, the compiler will pick which version or which type of loop, how you want to parallelize this. And so you had the freedom to the compiler had for doing the correct parallelization scheme, and that will help to write more portable code, because we're going to be using basically the smarts of the compilers and the runtimes to decide what's the type of parallelism that we want to use. And then you can make assertions that the iteration of the loops are completely independent, concurrent, and can be executed in any order. There is not monotonic type of the order that we have to execute the iterations. That's important to specify that. The other new feature that we have in OpenMP 5 is unified memory, and this is something that will help a lot whenever we have complex data types or complex data, array of structs or structs of arrays, and you want to map to the device, and you don't want to manage all of that using the map directives. You can use unified memory, and with doing that, all the memory is available in the host, is going to be available in the device or in the target regions, and then you can basically do the computations. Okay, so most important, so that's kind of like gives a little bit of an overview of what you will see in OpenMP 5.0. For more information, you should always look at the OpenMP website. We're going to have tutorials in OpenMP in Supercomputing 2019. We have a user meeting in OpenMP Con 2019 in New Zealand. Watch out for presentations there. We also have workshops upcoming that focus on OpenMP and other programming models for accelerators. And then we're going to have a booth in Supercomputing where we have different talks, and then people can meet there the developers or ask any specific questions about compilers or OpenMP, the way the specifications and so on. And with that, I finish my presentation.
Oscar, can you go back to the slide with the exercises? There's a question about that first tar file. Someone's claiming they can't find it. Is it posted?
We will, since we will ask people to run these examples. If it's not there, we can definitely put it in Slack.
And then the question is, what's the performance in comparison with CUDA?
It's going to depend from application to application. If a lot of the difference is if the compiler and the implementation can take advantage of the GPU shared memory. In some cases, the compiler can do the right optimizations and use that efficiently, and then the performance is very comparable. But if not, usually there is some sort of degradation because OpenMP 4.5 doesn't have an explicit way of saying map this to shared memory, in the GPU shared memory. Although in OpenMP 5.0, we're going to have a memory allocator that is going to help that. But what I see is like performance can be, like something like 30% or degradation, or in some cases could be worse than that if the implementation don't use efficiently the shared memory, the GPU shared memory.
What's the relative performance in unified shared memory? Is it slower than explicitly copying data?
Yes. It's always going to be slower because when we explicitly copy the data, we're kind of like transferring data in bulk. And So basically, we have seen that the performance is better when you use the map directive, where basically you're going to create the copies and then manage them yourself. Although in some cases, so the unified memory and all of that is usually implemented via the operating system or the runtime, who is going to manage pages, memory pages. So the same problem that you see with data affinity, like first touch policy, and also a next touch policy, or so on, you're going to be dealing with it. And so some implementations, you may have hints on prefetching some pages in unified memory that you can use to prefetch some of these memory pages to the accelerator of the device, but that's kind of like outside the OpenMP specification. That is there for convenience, but yes, we recommend to always use the map construct or the map clauses to basically to get good performance.
How do OpenMP parallel for loops, and especially OpenMP SIMD for loops, work in conjunction with compiler-driven auto-vectorization?
Yes. So for example, automatic parallelization basically, yes, has the compiler logic to decide if a loop can first be vectorized, and then if it's profitable to vectorize. So whenever you use like OpenMP SIMD, what you are doing is basically giving more hints to the compiler, and then but the compiler will basically use that with the existing auto-vectorization analysis to improve it. So in a way, the motivations of why we have SIMD, for example, in OpenMP is because we wanted to make vectorization more uniform across compilers. Like some compilers are very good in automatic vectorizations and others are not. So by adding that, we will give more information to the phases in the compiler generating vector code to do a better job. So they're meant to work together because it's kind of like hint to that, to the automatic vectorization pieces that we want to that the compilers use to implement vectorization. And yes, you can use SIMD inside the target region.
I think at that point, I'll call a break and thank both you and Helen for your presentations. I assume you'll keep